In the last subsection, we'll put these things together and use this fact that there's not too many binary trees and a short encoding for those to use the simple solution we've seen before with n log n preprocessing time on a slightly smaller instance. And then for the remaining bits, we'll have to use a new technique that you haven't seen so far called exhaustive tabulation. Just as a historic note, the technique is also known in the literature as the 4 Russians trick, which is a terrible othering term. So I'm refusing to use it. But you've seen it. If you see it in the literature, you should know what it's meant. So it's the same thing. Exhaustive tabulation is the 4 Russians trick. And, well, I mean, yeah, they were in the Soviet Union, not even clear if they were Russian. It's just a terrible name. So, but it's in widespread use, so you should be able to make the connection. One step is we already know an n log n solution. That's the sparse tables. And as I said before, it's enough if we can reduce the input size by a log n factor. If we can get the number of elements down to n divided log n, then the preprocessing time would be linear overall. So what we'll do is we'll use a blocking trick similar to some things we've done before. So we take our overall array and we use a judiciously chosen block size. Don't worry about the constants so much, but it's roughly log n numbers. And we treat those as a block. Now, what do we do with those blocks? From each block, we take the smallest element, the minimum in the block, and take that out as an element in this array B, which only contains the block minima. Now, if you look at the example here, I think it's to scale, but if you imagine the array gets much, much bigger, then this blue part is substantially larger than one block. This has roughly size n divided log n, because that's the number of blocks if I have roughly log n in each block, whereas the blocks are fairly small. So this B will be what we feed into our old algorithm with the n log n preprocessing time. So that we'll use here as our input of size m. So we use the sparse tables for this one. And what that means is with just using sparse tables as a black box, we can answer RMQ queries on the blue part, on the blue array alone in constant time. And we use linear time preprocessing, just because we've shrunk it just enough to be able to do that. Now, how does this help to answer queries? In particular, one easy observation, if I have a query that's just covering blocks entirely, then I could just translate that as answering the same query down here. And whatever is the answer is the overall minimum. That's fine. But in general, we will not have queries that are aligned with block boundaries. In general, we'll have something like this, a query that spans certain blocks entirely and then has an endpoint and start point somewhere in the middle of some other blocks. Well, we can still do some parts. So there's some range where it's entire blocks, and then there's at most one block at the outermost ends where we have to look inside blocks. And we'll use that to decompose our arrangement queries. Again, the overall argument is the minimum in the entire query range is one of those entries. So it can be what's the minimum in the blue part, or it can be the minimum of that green part, or the minimum of that green part. That's 3 candidates. And I can find which one is the ultimate minimum by just comparing those 3. That's the idea. That's how we get to constant time queries. But we still have to work out how to find the minima in these other parts. What's spelled out here is just the formal way to say the minimum from this, the minimum from this, the minimum from these blue parts. It's a bit a pain because the indices need to be shifted around. So I want this to be block local, whereas this is global. And so if you read it in detail, it just works out to be the overall index of the minimum. So we have only 3 possible values left to check if we can find the minima in the blue and 2 green blocks. And the blue block, as I just said before, is already done. All we need to do is find a range minimum in this smaller array. And for that, we can use our previous data structure, the sparse tables. What's left is the intra-block queries, where I'm just concerned about finding the range min in this tiny range within one block. Okay. We want linear preprocessing time overall. And we have to do a preprocessing step for all the n over log n blocks. So we really can't spend much time on each of them. And we also want constant query time. So we have quite a lot of blocks, but they're all super short. And in particular, the number of elements in a block is chosen so that with our encoding from before, we get a small number. So what does that mean? Each of these little blocks, for the intra-block queries, we only need to know the relative order within the block. So all we need to know for RMQ queries is this little Cartesian tree within the block. And such a Cartesian tree with 2b elements, we can encode with 2b bits. That was what we've done in the previous section. But 2b bits here, that's just 1/2 log n, because b is log n divided by 4. So the number of different Cartesian trees of that small size is at most 2 to the 2b, and that works out to be square root n. So the number of blocks is large, because that's that number. But the number of different blocks from the RMQ classes perspective is not that large. It's much, much smaller. Square root is much smaller than n divided log n. So we have many blocks that behave identical to all RMQ queries we can possibly ask. And so that's where this new trick comes in. Instead of trying to store for each block individually how to solve queries, we store once and for all possible shapes of the blocks, how they solve the queries. So we have something of the order of n squared different possible small problems, and we just write them all down. That's why it's called exhaustive tabulation. I don't know if my actual problem uses all of these problem types, but I don't care because it's not so many overall. So I'll just write them all down. What this looks like is one large lookup table. For example, we could have this little, if that was our tree, so if b was 4, I have 4 numbers in my block. That's one possible Cartesian tree. It has an encoding of 1, 1, and then 0, 0, 0, 1, 0, 0. So the block type here would be just that encoding. And you can treat that as a binary number and use it as an index in an array if you want. And then I have this entry a few times for all possible RMQ queries. For example, from 0 to 3, that one has 0, that's 3. The answer must be 1 because that's the lowest common ancestor. So I have one row in this giant table that looks like this. I have another row with the same block type and say from 1 to 3, that's for this range, and the answer is also 1. Then I have 2, 3. Here the answer is 2 because that's higher up in the tree, and so on. So you just have one row for each possible block type and possible I and j within the block. But this overall table is still not very large because the number of block types is square root n. The number of combinations for I and j is b squared, but that's log squared at most. So the overall number of rows is still fairly moderate, much, much smaller than n. And we can generate the table in linear time, and it uses much less than linear space. So to put it all together then, you can use that to answer the intra-block queries in constant time by storing for each block its type. So you can use that, look up the right row in your large table and look up the answer for the intra-block queries. And then with finding the minimum of the 3 candidates, you find the overall minimum. And so that in total gives you a linear preprocessing time and constant query time solution for the range min query problem. And from the discussion from the beginning of today, that gives you also a solution for longest common extensions in strings. Now, if you think about the problem just as it is, you can't really improve either of those two. Constant query time is, of course, best possible. You at least need to produce the output. And if you want constant query time, someone at some point has to read the array at least once. So the linear preprocessing time is also best possible. The solution surely is a bit complicated. Maybe that's an understatement. I don't know. If you've seen it a few times, it appears less and less mystical. But it's a combination of more techniques in one place than we've seen otherwise. Everything I told you today kind of came together for this final solution. And there's a few things that are still that you can still improve, and that's the space for the preprocessing. The time will remain linear, but you can try to improve on the space and reduce the constant factor in the space. That's something that I've worked on. But overall, that is the solution for range min queries, which closes the last black box from Unit 8 that we left open, and showed you a little bit of more advanced data structuring techniques, especially this bootstrapping from an exhaustive tabulation technique is something that often allows you to reduce the space by some logarithmic factor. And so that's what's used in modern solutions for text indexing. They're based on what we've done in Unit 8, plus they further compress the size to handle the large data sets we have.